Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 13, Atomic Structure, Part 6. This is the last video in Chapter 7 of your textbook. Here are our objectives for today's video. Pause here. So this video, we're going to talk about shortening our electron configurations and also some exceptions to the Aufbau principle. So notice how it's called the Aufbau principle and not the Aufbau law, and that is because there are exceptions to it. So Hund's rule just states that the lowest energy, most stable electron configuration for an atom is the one with the most number of unpaired electrons, which just means the highest number of electrons that have spin up that don't have a spin down in the same orbital with them when we draw the orbital diagram. And this will help for us to account for the cases where there are exceptions to the Aufbau principle. Pause here. So there's only one application of Hund's rule that I'm going for you to expect that you are able to do. And what that is, when we have an S and a D that are the last two in a set, we may be able to move electrons from the S to the D in order to maximize our unpaired electrons. And when I say maximize the number of unpaired electrons, what I really mean is to get a D5 electron configuration. So notice that Fe2 plus, how we did this yesterday, or the last video rather, it would end with S2D4. But what you can actually do is you could take one of the electrons from the S, move it to the D, and then I have S1D5. That's the only time that I am going to expect for you to apply Hund's rule. It's not as though there aren't other cases where it applies, but this is the only time that I expect for you to do it. Pause here. So in the last video, we talked a little bit about the valence versus the core electrons. And then we can actually, instead of writing all of this out, and when you were doing the problem set for the last video, you were probably wishing that you could just like have a placeholder in for some of them. And I wanted for you to have that feeling such that you would feel a little relief when you see that you're allowed to shorten these. So not only are you completely allowed to shorten them, but sometimes I'm going to require it. So I might say only showing valence electrons. You can shorten it. It can only be a noble gas in the bracket. It cannot be any other type of element. And the reason why is because this shows us just the valence electrons, meaning the ones that actually participate in bonding. Pause here. So the first one is Cr5 plus. All right, so I go and I find chromium on the periodic table. Chromium would normally have 24, but then it has a 5 plus charge, so it has 19 electrons. So it's going to have the same electron configuration as potassium. So I can just do this shorthand. So I'm going to do argon because it's a noble gas right before it, and then potassium is in the fourth row so 4s1. I don't have to do any sort of switching for that. Now for iron, it would normally have 26, but I have a 3 plus charge. So that is going to have 23 valence electrons, which is the same as having vanadiums. So start with argon. And then for S2, 3D, 3, but I can then move things around to get that D5 configuration. You could either leave it as 4s0 or just leave it out entirely. 3d5. And then Br minus. So I would normally have 35 electrons, but I'm going to be adding 1. So 36 electrons, which is the same as krypton. So you actually cannot just list it as krypton, even though I completely understand why you would want to, but that doesn't show us the valence electrons. So you have to do argon plus everything else. So argon for S2, 3d10, or P6. I do allow students in the 10 and the 10H class to just do krypton, but since the College Board doesn't allow it, and this really is a pre-AP class, that's the reason why I don't, though it's not completely incorrect to do so. All right, that's all for tonight. Thank you so much for watching and have a great night.